Hi everyone to the second segment of the course, pre-processing. In this part, we will start by talking about the meshing. We will see how you generate meshing in OpenFoam and then move on to boundary conditions. We will see how you can implement them correctly in OpenFoam. Before we dive into the details of meshing, let's go over some key terms that you want to know when working with mesh. Domain, which is where the fluid flow takes place. Cell is the control volume into which the domain is broken up. Face is the boundary of the cell. For example, here a hexahedron cell has 6 faces. Faces can be boundary faces that border only one cell, or internal faces that connect two cells together, which is like a face between two cells. Edge that connect two nodes together. And the cell centers. Last thing, maybe the face center. So these terms that you need to know what they are and to be able to visualize them, because you will hear this terminology a lot while you are dealing with meshing. This is why we need meshing tools to generate this data for us, which we later use to discretize the equations with finite volume method techniques. To generate these data, OpenFoam has two mesh creation tools, blockMesh and snappy hex mesh. But you still have the freedom to create mesh using your favorite meshing tools and then import it to OpenFoam using conversion mesh utilities that are available in OpenFoam. In this video, I explain the blockMesh utility in detail. I think now we are ready to explore the blockMesh utility. So we open a terminal and do the regular stuff as we used to do. We go to run directory and copy a tutorial to explain this blockMesh file. For this purpose, I think cavity flow is suitable as it's the simplest mesh topology you're gonna see in OpenFoam. And here you see all the input files. I just need block mesh dect. You can delete the others if you want, but I will keep them. It's okay. Let's open the case directory in this window as well for a demonstration purpose. Now we open the block mesh dect dictionary. And here you find all the settings needed to create the mesh. So let's run blockmesh command to see what we will get. You run the command in the case directory here. Here you can see these subdirectories. Otherwise, you will get errors. Say you run it in the system directory, you will get this error. So let's go one level higher and run the command. And here you see the mesh is generated. We will open these files later. If you want to delete the mesh data for any purpose, you can use foam clean tutorial script to do this process for you. As we are talking about where to run the command, actually there are other ways. For example, you write the command anywhere and follow it by the case location using case option. And here we go. And here you see the mesh is generated. To visualize the mesh, you can use parafoam script, which will create a .foam file and export it to the ParaView software. we see the grid of the desired domain as it is specified in the blockMesh dict. In the blockMesh dict, we specify the size of our domain using which is so-called vertices. So for this block, we need only 8 vertices. To be able to visualize these vertices, you can open the user guide. You find this case in chapter 2. And here you see a schematic for the geometry and the boundary condition. The book will take you from the pre-processing to the post-processing. You must read that. Here you see the representation of each vertex. There are also many scripts available you can use to visualize your domain. There is a script in OpenFoam called display blockMesh. It takes the file name as a parameter and plots the domain for you. You can even change the input file from here. For instance, say you want to increase the distance in the z direction. So to understand how the block is represented, you can use this script here or back to the user guide. Okay, go again to the blockMesh dict dictionary. The first user input here is the scale. For example, if your domain is in centimeter or in millimeter, you write it as it is in the vertices, but adjust your scale to convert it to a meter, which is the unit OpenFoam uses here. And then you specify the vertices. After that, you tell blockMesh to connect these vertices to create the domain. Then you specify the number of the cells in each direction. For instance, say I want 30 cells in the X direction. And run the command again to override the mesh. Refresh bar view. Look what will happen to the mesh in the X direction. Let's exaggerate. Say 50 cells in the X direction. Okay, let's change it back. And now I think the difference is clear. Okay, we move on to the gradient. This case use a simple gradient. These numbers are the total expansion ratio in each direction. This is the ratio between the length of the largest cell to the smallest cell. Let's try some ratios. And here you see the length of the largest cell and the thinnest cell. You can do that in all directions. We continue. Here edges where you define how the vertices are connected, like by arc or a straight line. By default, it's a straight line. so I keep it. Then you define the domain boundaries by giving each boundary a name, a type, and then specifying which face represents this boundary. These numbers here are the index of the vertices that represent the moving wall boundary. For number 3, for example, is this vertex here. You can go back to the book or this tool to help you write the vertices of the boundaries. For the moving wall, for example, we have 3, 7, 6, and 2. For the fixed walls, we have 3 faces grouped together. They are 0, 4, 7, 3, and 2, 6, 5, 1. The last one is 1, 5, 4, 0. And so on for the front and back. You can refer to this chapter here to visualize the vertices. While I was recording this video, I remembered this tool. This one can help you with the gradient calculation. I will leave the link in the description. For instance, say you had the size of the domain in a specific direction, the number of the cells, and the length of the first cell that you need. This tool will calculate the expansion ratio for you and the length of the last cell. Or maybe you need a specific length for the last cell instead. So let's try this one in the X direction. And as you see, if the ratio is larger than 1, the first cell will be the smallest one. Watch that in the Y direction. Okay, before you start generating mesh in OpenFoam, there are some things that you need to know. Number 1, OpenFoam always uses 3D meshes. Even if the simulation is 2D or even 1D, you still need at least one cell in each direction. For example, cavity flow is 2D simulation, but we still have to set just one cell in the third direction. And to tell OpenFoam to not solve for this direction, we set the type of the boundaries in this direction to empty. In our case here, we set the front and the back boundary type to be empty, which is normal to the flow direction. Number 2, I think you noticed that the numbering in OpenFoam starts from the 0 index. So the first vertex here has a 0 index, the second is 1, and so on. The next thing that you need to know is that the order of writing the vertices that generate the block or the domain does matter. If you change the order, it will not work. Let's try. Here you see the error. The error is in this line. So let's change it back. You must start with the vertex that makes it look right-handed. In this example, the vertex 0 achieves this. So second step after you specify the origin, you put your right hand on the 0 point, your thumb pointing to the Z direction, and the rest of the fingers rotate in the direction that defines the rest of the points. After you write the points of the back face, you write the projection of the points in the front face in the same order. And for the boundary faces, also should be written in a specific way. The order doesn't matter, you can start from any point, but the direction should be counterclockwise direction. This is if you are looking at the face from the outside, as you see here in the right. If you are looking from inside, the direction will be clockwise. You can also use your right hand where your thumb pointing outward, normal to the face, and the rest of the fingers rotate in the wanted direction. I think that's enough for today. We continue next video. We will look at a real example and explore how to think about the mesh step by step. Thanks and see you.